Today in this video, I'm going to explain Monge's method. This is a method which is used for solving differential equations of the form RR plus SS plus TT is equal to V, where small r, st have their usual meanings and capital R, st and V may be some functions involving x, y, z, p and q. Here in differential calculus, p stands for partial derivative of z with respect to x, that is del z over del x. Q stands for partial derivative of z with respect to y, that is written as del z over del y. R is used to denote del 2z over del x squared, that is the partial derivative of p with respect to x. S is equal to del 2z over del x del y, that is partial derivative of q with respect to x. And t is equal to del 2z over del y square, that is the partial derivative of q with respect to y. So these are standard notations used in partial derivatives. So now let the given partial differential equation is capital R into small r plus capital S into small s plus capital T into small t is equal to capital V. Say equation number 1. As we know, that dp is equal to del p upon del x into dx plus del p upon del y into dy, which may also be written as, since the del p over del x is the partial derivative of p with respect to x, that is del 2z over del x square, so that is equal to r. So r dx, and similarly del p over del y is s, so plus s dy, since p is equal to del z over del x, so we differentiate p partially with respect to x, and q is a partial derivative of z with respect to y. Now say del p upon del x means del 2z upon del x square, which is denoted by small r, and similarly del p over del y is equal to del 2z over del y into del x, which is denoted by small s. So dp is equal to r dx plus s dy. Let it be equation number 2. Similarly, we may find dq is equal to s dx plus t dy. Say it is equation number 3. Now, let us find the values of r and t from equation 2 and 3 in terms of s. So r is equal to dp minus s dy upon dx. Say this is equation number 4. And now from equation 3, t is equal to dq minus s dx over dy. Let it be equation number 5. Now substituting the values of, now putting the values of r and t in equation 1 from equation 4 and 5, we get r into dp minus s dy over dx plus capital S into small s plus capital T, and small t is equal to dq minus s dx upon dy is equal to capital V. Now we have to multiply both sides of this equation by dx dy. So we get r dy bracket dp minus s dy plus capital S into small s dx dy plus capital T dx bracket dq minus s dx is equal to v dx dy. Now opening the bracket, we get r dy dp minus r s dy square plus s into s dx dy plus capital T dx dq minus capital T into s dx square. I forgot to write dy square here. So is equal to v dx dy. Now transposing all the terms having small s on one side of equality and keeping the rest of the terms on the other side, we get r dy dp plus t dx dq minus v dx dy is equal to, so is equal to r into s dy square minus capital S into small s dx dy plus t into s dx square. So r dp into dy plus t dx into dq minus v dx dy is equal to, taking smallest common out of all these terms, we get in the bracket r dy square minus capital S dx dy plus t dx square. The above relation may be possible if and only if the values of this expression and this expression are 0. So r dp dy plus t dx dq minus v dx dy is equal to 0. Let it be equation number 6. And r dy square minus capital S dx dy plus t dx square is equal to 0. Let it be equation number 7. Now, if equation 7 is resolved into two linear equations in dx and dy such that dy minus m1 dx is equal to 0, let it be equation number 7, and dy minus m2 dx is equal to 0, let it be equation number 9. Now, using equation 8 and equation 6, and if necessary, the equation dz is equal to p dx plus q dy, we may find or we may obtain two integrals, say u1 is equal to a and v1 is equal to b. Then u1 is equal to f v1 is called an intermediate integral. Proceeding in the same way with equation 9 and equation 6, we may find another intermediate integral in the form u2 is equal to fv2. From these two integrals, we may find the values of p and q and then putting these values in these values of P and Q in equation dz is equal to P dx plus Q dy, and integrating, we get the required solution of the given partial differential equation. In order to clarify the concept here, we would like to take an example. Example, solve r is equal to a squared t. Solution, the given partial differential equation may be written as r minus a squared t is equal to 0. Now comparing with the partial differential equation rr plus ss plus tt is equal to we get capital R is equal to 1, capital S is equal to 0, capital T is equal to minus a square, and capital V is equal to 0. Thus, Monge's auxiliary equations that is r dp into dx dp into dy plus t dq into dx minus v dx into dy is equal to 0, and r dy square minus s dx dy plus t dx square is equal to 0 become dp dy minus a square dq dx is equal to 0. Let it be equation number 1. And dy square minus a square dx square is equal to 0. Let it be equation number 2. Now here the equation 2 may be written as dy plus a dx into dy minus a dx is equal to 0. It implies that dy plus a dx is equal to 0. Let it be equation number 3. Or dy minus x a dx is equal to 0. Let it be equation number 4. Now, integrating equation 4, we get y minus ax is equal to c1. Let it be equation number 5. Now, from equation 4, dy is equal to a dx, putting in equation 1, we get dp a dx minus a square dq into dx is equal to 0. Now dividing both sides by a dx, we get dp minus a dq is equal to 0. Now integrating integrating P, we get P is minus AQ is equal to C2. Let it be question number 6. Thus, one of the intermediate integrals is P minus AQ is equal to phi of C1, since C2 may be written as a function of C1, or P minus AQ is equal to phi, and C1 is equal to y minus AX, so phi y minus AX. Let it be equation number 7. Similarly, the second intermediate integral is P plus AQ is equal to f y plus AX. Let it be equation number 8. Adding equation number 7 and 8, we get AQ is cancelled by minus AQ, so we get on left hand side 2P is equal to, on right hand side, phi y minus AX plus f y plus AX. Let it be equation number 9. Now, subtracting equation 7 from 8, we get, now on subtracting, P is cancelled by P, and AQ plus AQ, 2AQ is equal to, on right hand side we get f y plus AX minus phi y minus AX. Let it be equation number 10. Or Q is equal to 1 upon 2A f bracket f y plus AX minus phi y minus AX. Let it be equation number 10. Now, since dz is equal to p dx plus q dy, putting the values of p and q in this equation from equation 9 and 10, we get dz is equal to half f y plus ax plus phi y minus ax into dx plus 1 upon 2a bracket f y plus ax minus phi y minus ax bracket close dy, or dz is equal to now opening the bracket, half and dx will multiply both the terms and we get half f y plus ax dx plus half phi y minus ax dx, and here 1 upon 2a and dy both will multiply. We get half 1 upon 2a f y plus ax dy minus 1 upon 2a phi y minus ax dy. That is equal to 1 upon 2a f y plus ax dy plus a dx, and taking 1 upon 2a common out of the two terms having phi, we get minus 1 upon 2a phi y minus ax bracket dy minus a dx. Now taking 1 upon 2a common, we get dz is equal to 1 upon 2a bracket f y plus ax into dy plus a dx minus 1 upon 2a we have taken common phi y minus ax into dy minus a dx. Now integrating both sides, we get z is equal to 1 upon 2a psi 1 y plus ax, because assuming y plus ax as t, if we differentiate we get dy plus a dx. So we get some function of y plus ax. So phi 1 y plus ax minus 1 upon 2a phi 2 y minus ax, where psi 1 and psi 2 are some arbitrary functions of x and y.